Hello everyone, welcome to this lecture of computer system security. Today we're gonna start our next lecture, which is about cryptography and hash. This is a very important and at the same time very interesting topic that we're gonna talk about. It probably takes maybe 3.5 weeks from us, and we'll be talking about this topic. We'll be talking about some basic definitions and terminology and expectation that we have from cryptographic algorithms. We talk about two major classes of cryptographic algorithms or encryption algorithms, symmetric and asymmetric encryption. And we say how the encryption algorithms will be used in order to make sure about the confidentiality of a computer system. And also we say that how they can be used for message authentication as well. It means that, or for authentication, it means that you use the encryption not for confidentiality, which is the base or the primary application of cryptography, but it can be also used in order to attain the authenticity or authentication in computer system. And we also talk about public encryption algorithms or asymmetric encryption algorithms. And we end with hash functions and secure hash functions, that there are some type of scrambling which are close to encryption or cryptography. Okay, let's get started by talking about the origin of the word cryptography. Cryptography is a Greek word originally, and it means secret writing. It means that you write something in a secret way. So some researchers, some historians believe that cryptography first started in the ancient Greece, and some other believe that cryptography started in the ancient Egypt in 1900 before Jesus Christ birth. And they believe that the ancient Greek scribe used to use some type of cryptography in order to somehow encode the information they wanted to write. And hieroglyph characters are good example of that. For example, you want to write something, you don't use letters A, B, C. Of course, they may have had different types of letters. But let's say, for example, if this stands for A, if this is your first letter of your alphabet, you don't need to use it as is. You can encode it, or you can hide it by substituting it with some hieroglyph characters or hieroglyph symbols like this. Assuming this text here, or this series of symbols, it means, for example, you alone are blah blah. This is a part of a bigger text. I didn't want to bring all of it because that's of course not a part of our course. But yeah, this, if you look here, this symbol which is here, it stands for Y, and this one here, which is here, it stands for O, and so on. So the basic application of cryptography or encryption, I'll be talking about the words cryptography and encryption. I'll be saying that they are synonym, but let's for now continue. The basic application for cryptography is to make sure about the confidentiality. In fact, this is a definition that we can use it as a formal definition for cryptography. We say that cryptography is a practice, is a practice or a set of practices that tries to provide confidentiality for data transmission or for data storing. What does that mean? It means that you may want to send data somewhere, and of course, the medium, whatever the medium is, it might be air, it might be network, or it might be, for example, in ancient Egypt, it might be over some written papers or whatever. They want to send it somewhere, but you want to make it confidential between a few set of people or few set of individuals that are supposed to just understand the meaning of that text or that letter. So you want to keep it confidential, and you want to transmit the data, or you want to store the data somewhere. For example, you want to store your data in your hard drive, but you are not sure about if you can physically attain the security of that hard drive. That hard drive someday might be stolen or something, but you have some very important information on it. So you, before storing the data on the hard drive, you encrypt the data, or you use cryptographic algorithms in order to encode the data. And that way, even if I'm an attacker, I get physical access to your hard drive, I cannot ultimately read the data because they're encrypted. So that's why we say that the basic application of cryptography is to provide confidentiality. And here are a list of terminology that we should know about cryptography. We have plain text versus ciphertext. Plain text is a text that we want to encrypt it, we want to code it, and the ciphertext is a text or the data which is just encrypted or just coded. And then we have encryption. Encryption means the action of encrypting the data. But sometimes encryption is being used as a synonym of cryptography. When people say cryptography or cryptographic algorithm, sometimes they say encryption or encryption algorithm. There is another term for that that will be showing you in the next slide. And here is the whole process that we see. We get the plain text. The plain text is a normal readable text or data. It might be text or data, whatever. And then we encrypt it using some encryption algorithm. And then what we get is called ciphertext. And then sometime later, it might be the person who encrypted the data, or it might be another person who is the recipient of the data, which is also allowed to be or authenticated to be able to use the data. We or that person, we apply some decryption, and then we retrieve or recover the plain text. So terminology that we need to know, and I'm going to give you kind of official definition about them. The first thing is plain text. Plain text is the original unencrypted message, text, or data. In general, we say data because you know, at the end of the day, when it doesn't matter when you have message or text or data, whatever, it's going to be stored as a data in somewhere in your auxiliary memory, or either in your main memory. So at the end of the day, it's a sequence of binary data. But plain text, what we are emphasizing when we say plain text, it means that this is the original data. It's unencrypted. It's not protected, and it's kind of easy for the attacker to use it because it's not protected. So it might be the original unencrypted data, or the data which is just being decrypted successfully. Because at the end of the day, when you do this process here, you decrypt, and again you get the plain text. So the plain text might be the original data, or data came out of the successful decryption. We have ciphertext, which is of course the encoded version or the decrypted version of the message or the data or the plain text, let's say. And one important parameter that we have it in almost all of the encryption algorithm is called key. Key is actually a string of numbers or characters, which is noun only, which is provided to only the sender and the recipient, or to a set of legit people, legit individuals or users. And the key, like you see here, the key will be used in the encryption process, plus the decryption process. So we get the message, we get the plain text, we use the key and apply it to a specific algorithm. We encrypt it. What we get is plain is ciphertext. The ciphertext now is ready to be transferred, to be transmitted over an insecure media. It might be network, it might be air, it might be a disk, whatever. And then the other side, we get the ciphertext. We apply the decryption algorithm using the key. I would say using the same key, not for all encryption algorithms, but for some of them, the encryption key and the decryption key are same. So, and then we get the plain text or the original text. So the key is a string of numbers or characters which is being used in both encryption to get the ciphertext and to drive the plain text from the ciphertext. Okay, we have key space. Key, like I said, is based on the definition, is a series of or string of characters or numbers. And at the end of the day, you know, every character in a computer system, it takes 8 bytes. I'm sorry, 8 bits. So if you say, for example, the key is 64, let's say 8 characters, to me, it means that the key is 64 bits because I'm gonna multiply 8 by 8 and get them. So the length of the key in terms of characters, whatever it is, at the end of the day, is gonna be translated into some bits. And let's assume that, for example, our key is 64 bits. We have a key of 64 bits. So 64 bits that we have in our key, what are going to be the total amount of key that I can use in this space? Of course, you know, every single bit, if you're talking about 1 bit, that or maybe 2 bit, every bit position might be either 0 or 1, and putting together 2 bits to a space, it gives me 2 to the power of 2 or 4 different combinations. The same thing for a key with the length of 64 bits, the total amount of keys that we can generate using 64 bits is 2 to the power of 64, which is, of course, you may say that this is a big number. Yeah, it is, but we'll talk about it. For encryption, for cryptography, it's not that great, to be honest. Anyway, the total number of keys possible for a cryptographic system is called the key space. The reason we define key space and the reason key space is important for us, we'll talk about the there is one known and very important attack, which is called brute force, at which the attacker comes and try to apply all possible keys. So all 2 to the power of 64 keys, the attacker tries to apply all of them and try to see if he or she can decrypt the data, which is, of course, if successful, it means that he or she has broken into our system. But for that type of attack, it's important to see what is the key space. So the bigger the key space, it means that the system is safer or more secure. Okay, we have cipher or encipher, which is also called encryption or cryptographic algorithm. Cipher or encipher is the encryption method or encryption algorithm plus the key. The encryption algorithm and the key together, they make the cipher. So which is key, of course, is something constant and or given. So you have the cryptographic algorithm implemented or either in hardware or software, and the key, that's called cipher or the process of encryption. And then decipher or decryptor or decryption is the opposite. It is the process that decrypts the data. So it is the decryption algorithm plus the key. Okay, we're done with the terminology. Now I'm going to talk about one very important, super important classification in cryptographic algorithms. We have two major classes of cryptographic algorithms. The first is called symmetric key cryptography, or uh, symmetric key cryptographic algorithms, at which the same key, this is a very important feature of this type of encryption, the same key is going to be used at the sender side and for encryption, of course, and at the receiver side for decryption. So if you look at this chart, it shows that, for example, we are assuming here the computer A is trying to encrypt some plain text, some data, and then of course it gets the ciphertext after encryption. And A is willing to send the data over the network to computer B. And computer B gets the ciphertext, applied in decryption, and retrieve the plain text, and now plain text is ready to be used by B. Of course, there are some other computers here, like C, for example, that they also may get the ciphertext, but they don't have the key. So see if there is any other computer which should be, because we are talking about the network, there should be many other computers other than B and A here, but none of them will be able to decrypt the information or the ciphertext because they don't have the key. And here you see that the key, two important things about the key here. First, the key is available only to A and B. So this is a secure communication between A and B, secure transmission of data between A and B first. Second, A and B are both using the same similar key. So A and B are using one identical key. That's a very important feature about symmetric key encryption algorithms. And of course, this assumption makes development of these type of encryption algorithms easier, but it arises a very important, super important question. And that question is this: okay, this key is something important that should be shared between A and B. How are we going to generate, which is important but not that important, and this is the most important part, how are we going to, after generating the key, how are we going to share it between A and B? Of course, we generate the key either at computer A or computer B, and one of them is supposed to send the key to the other one. So before having the key, there is no encryption. So we are supposed to send data over an insecure media, and we don't want to reveal the key to all, because that's going to ruin all of our future efforts. So the symmetric key encryption actually has no answer to this, for except very few cases. There is no answer in symmetric key encryption algorithms for this question. But in contrast, we have another type of cryptographic or encryption algorithms, which are called asymmetric key cryptography, or sometimes they call it public key encryption. And here in this type of encryptions, we have two keys. You see, here is the first key, and here is the second key. For the communication between A and B, there is no key which is secret between A and B. B has two keys. One of them is called B's private key. That's the private key of B, that the only person, the only computer which is aware of that is B. And this is something very important. B generates this and keeps it for itself. It doesn't reveal it to other person. B generates this key, this black key, and keeps it for itself. But also B generates another key, this blue key, which is called public key, and publicize that key to everyone. So everybody would have access to this B's public key. This blue one, you see, it says to the public. So everybody would have access to that. So now A is one of them, A is one of the, let's say, whole network. A wants to send some encrypted information to B, A uses the B's public key to encrypt the text and then get the ciphertext. Here, the ciphertext is encrypted, is locked with this key. But based on the nature of these algorithms, this type of encryptions, the ciphertext cannot be retrieved, cannot be kind of decrypted using the same key. So this key is only good for encryption. It's not good for decryption. It is not like the previous encryptions that the same key can do both encryption and decryption. No, here this key only can do the encryption. So it can produce ciphertext, and then of course A sends the encrypted or ciphertext over the network. B receives it, and then now B has access to its own private key. Use that private key to open the to apply the decryption to get the plain text extracted, and then B reads the data and use it. So this is called asymmetric, or sometimes, since we have two keys, private key and public key, sometimes people call it also public key encryption algorithms. So public key or asymmetric, they both refer to the same thing. Okay, here's kind of another graphical representation, which is basically the same thing. It shows that we have two types of algorithms. Symmetric uses one type of key at both encryption and decryption side, or sender and receiver. Of course, you know that we are talking about sender and receiver, and here you see all the time network, but it might be at one local computer when you are encrypting some information in order to store it in your, let's say, for example, local hard drive, and then later you want to retrieve that data. So one direction is encryption when you want to store the data, when you want to save the data, and another way is decryption when you want to read the data from your hard disk. In modern computer systems, basically, this even may happen between the processor and the main memory, because in modern processors, we have many processes at the same time that they have access to main memory. So some processes may have some sensitive and important information. So before they transfer the information from CPU to main memory, here, if this is a CPU and this is a main memory, yeah, the CPUs encrypt the data and put it in main memory. And next time the CPU reads the data, it should be decrypted first. So of course, in most of our example, we say sender receiver, but like I said, it doesn't mean that we are only limited to sender receiver or network situation. Encryption and cryptography can be applied when you want to store the data in auxiliary memories like hard disk, or even when CPU wants to interact with the main memory because of security condition, CPU is willing to encrypt the data and then decrypt it. Anyway, here we have one key in symmetric, and in asymmetric encryption or cryptography, as you see, we have two different keys. One is only good for locking, and the second one is good for, of course, locking and unlocking, which is here used for unlocking. Okay, cryptography or encryption algorithms are, of course, you have heard about them, but we want to see that what are the actual places that or the applications that we can see the application of cryptography. I would say there are many applications. I just here pointed to a few of them. For example, in web traffic, when you're using HTTPS, that S stands for secure connection, and that security is provided through some encryption. Your data between the data which is being transferred between the web server and the web browser, it's being encrypted, which is good. In wireless traffic and wireless network, they may use WPA2 or WEP, or in Bluetooth, which are encryption algorithms and encrypt the data in order to make sure that because wireless data, by nature, it is broadcast. It means that if I'm connected to, let's say, a wireless node or access point, whatever, and you are connected, by nature, we can see we can see each other's packet. I see your packet, you see my packet. So there should be some type of protection, and encryption is a very good thing for that. Like I said, you can encrypt and decrypt the files that you want to store on external or auxiliary memories. It is used also encryption used for content protection, for example, in DVD discs or Blu-rays, which is sometimes good for kind of enforcing for copyright. You want to make sure that the music or the movie that you have produced is safe and no one copies that. You can encrypt some portion of that. You don't have to encrypt all of that. Access control. These are all of these applications here. They somehow points to the case that we use encryption for attaining confidentiality. We want to keep our data confidential, but encryption also can be used for authentication and authorization. You get something, you get a message over the network, and you want to make sure that this message comes from here. For example, let's return to this. You want to Bob wants to make sure that the message came from Alice. Yeah, here Bob wants to make sure that the message came from Alice. So of course, if it decrypts it and gets something meaningful, it means that the message came from Alice, because Bob and Alice are using the same key. So we can here make sure that this is Alice sending something, which means authentication. We can authenticate the sender, and also it might be used for authorization. Okay, based on these things, cryptography is a very powerful and tremendous tool that is the basis for many security solutions and mechanisms. But we should make sure that we at the same time we know that cryptography or encryption is not the solution for all security problems. There are some cases, or I would say many cases, that encryption cannot help. You can, for example, if you remember in the previous lecture, we've talked about many malwares. You can pause the video here and think about and find at least one of those malwares that encryption or cryptography is not helping to kind of protect against them. Okay, you have paused the video and you have thought about this. Please use this word everywhere with the same exact kind of spelling and lowercase, uppercase as the attendance goes for today's video. Thank you. Okay, about that example, that cryptography is not good for helping us. For example, we can point to DDoS attack. In the DDoS attack, if you remember, we said that you have many bots which are or many computers which are compromised, and those computers are going to be used by a commander, by a server, in order to, for example, apply any type of DOS attack. It might be TCP sync, or it might be ping flood, whatever. Okay, let's say you have a system that you have for example, social media for some group of people, and everybody is supposed to come and make an account or create an account if they want to use that thing. Of course, the messages that you transfer or transmit between the user when you want to give them the service or when you want to let them create an account, all of them are encrypted and are safe. But all of the bots that you have in that botnet, they can use the encryption and they can create the accounts. They have, let's say, 100 different accounts, which are all created by the bots, and they're all encrypted safe. And encryption here is good to make sure that the data is being transferred between the server and the bots in a safe or secure way. Yes, that's correct. But when they start the attack, when they start the DDoS attack, the encryption cannot help because they have already authenticated, they have already, they are sending, receiving data in a encrypted manner. Yes, that's right. But that encryption doesn't let them, doesn't prevent them from the attack. So the encryption here is not helping us. It actually even makes it worse because that encryption and decryption process may take a little bit more of time from the server. Another thing about cryptography that we need to know is that cryptography or encryption algorithms, they are reliable uh, and they would help us in order to improve our security, or let's say in particular the confidentiality. But there are some cases that this might not be achieved because of the implementation or the way that the user is using the encryption algorithm or encryption method. Look at this figure here. This is a very kind of simple and nice one. You have here a lock that protects this specific shelf of this driver, and of course this is protected, and there is nothing wrong with this lock. But the designer that have used this, he or she didn't pay attention that, okay, this one can be pulled out, and now I have access through here. A very easy access, and I can see or access all of your assets or all of your data that you have here. The same thing applies to encryption. When you design an encryption algorithms on a paper, and you design the algorithm, they might be safe, they might be 100% secure. You can, for example, for DES algorithm or for AES algorithm, let's talk about AES. The key is 128, and the key space is very big, 2 to the power of 128. 2 to the power of 128 is not small. We'll talk about it, that even brute force, it takes many years. It's impossible. But when you implement it on a chip, there's some side information, like, for example, the power consumption of the board. The power consumption of the board will be somehow related to the key, and we can break into the algorithm by just looking or analyzing the power of the power consumption of the chip or the board in order to extract the key. Of course, it's not going to be easy, but it would help us to reduce the key space, or to, in a very, very significant way. This is something which has been done, and researchers have shown that, okay, in using some side information, side channel information, like power, for example, they could have break into AES even encryption algorithm. So yeah, the implementation and the way we use it, way we use the encryption algorithms or cryptographic algorithms also matter. Okay, here is a kind of math model of symmetric encryption algorithms. We get the plain text X and the key, and here we have the encryption algorithm E, and this encryption algorithm E, we can see it as a function. It takes X and K as input, and it produces Y. So Y is actually the output of the function E, which is encryption, and K and X are the inputs of that encryption. And then at the receiver side, we have X, which is the plain text or the retrieved plain text, which is the D of K and Y. So this Y, which is the encrypted one, encrypted data or the cipher data, is going to be applied to function Y plus the same thing plus the key K, and then the decryption again is another function that works on these two inputs and produces the X, which is the plain text. Okay, these are well-known symmetric encryption algorithms that we'll be talking about them in this lecture. Data encryption standard, or DS, triple this, which is 3 times repetition of DS, and then we have advanced encryption standard, or AES. Okay, before getting into the real encryption algorithms and talking about them, I'm willing to also talk about some principles and some features about cryptographic algorithms. The first thing is called Kirchhoff's principle. We've talked about this principle in the lecture number 1, and if you remember, we have one of the fundamental security principles. We said it was open design, and in open design, we said that everything in a security countermeasure should be open. The actual name for that is Kirchhoff's principle. It says that in a crypto system, everything should be open. Everything should be made public to people, and that includes the details of the algorithm, the encryption algorithm itself. The only thing that we can keep it secret, we don't have to reveal that, is this key. Everything except the key should be kept or should be made public. And I explained this. I told you that, for example, if I come up with some encryption and encryption algorithms, and I say that, okay, I don't want to give you the details because detail of that is something that if you know, you can use it against me. Okay, that's not a good countermeasure, because now I have to somehow protect my design details, my design files, my design information. And if that encryption is really used somewhere very important, now how am I supposed to make sure that no one, for example, comes and steal that physical papers or file from my computer? So we are basically shifting the problem from the one place to another place. We are not solving it. So everything about the cryptographic algorithm should be open, should be made public, except the key. Okay, let's talk about brute force first, and then I'll get back to this. Brute force attack is a very important type of attack in encryption that says attacker comes and applies all possible keys, or in another word, attacker spans or scans the key space. It means that all possible keys are going to be applied one by one to the encryption system by the attacker in order to get the ciphertext decrypted. Of course, the attacker doesn't know which one is the key. For example, if your key is 64 bits, you're gonna start from all 0 to all the way to all 1, which is of course a very big number. If I'm the attacker, I have to apply many keys, 2 to the power of 64 different keys. But let's assume that I have that capability and I can apply them one by one. So this is called the brute force. Of course, I might be lucky, I'm an attacker person. I might be lucky, and the first key that I apply is the key that you actually used it. And in the worst case, I might be very unlucky, and the last key, the very last key that I apply is the key that you used it. So this is a best case, this is a worst case. Of course, we don't look at best case and worst case, we look at the average case. This follows the binomial probability distribution function. And if you find the mean for that, you'll find it very easy that the average number of trials that the attacker might need to apply in order to get the key or in order to find the key is on average half of the key space should be spanned. So if the number of keys are 2 to the power of 64, half of that, which is 2 to the power of 63 keys, should be applied on average, of course. Okay, this is brute force. Having this said, we say that, okay, encryption algorithms or cryptographic algorithms, they can somehow protect our data for a given amount of time. Because of course, at the end of the day, you have some number of bits for your key. If it's 64, 128, 256, whatever, 2 to the power of that number, something related to that, to the size of that key, you have a limited, at the end of the day, whatever the size of your key is, the key space is going to be limited. And if I'm an attacker, I start from the very first one to, and I continue, and at some point, I'll be able to find the key. So we say that encryption algorithms, they are, I don't say all of them, but almost all of them, they can be broken. They can be kind of through using the brute force attack, of course, they can be broken. So the important thing here is how long does it take for the attacker to apply the brute force attack? The goal for the encryption algorithms or cryptographic algorithms is that make the cost or the time required to apply a successful brute force attack. The goal is to make that cost or that time greater than the value of the protected information. I have a piece of information which is being protected. Let's say I have 1 Bitcoin, and that Bitcoin is protected somewhere. It worth, for example, let's say 40,000. If for getting that key, for finding that key, you need to you need to pay something more than $40,000. It means that I'm safe, I'm secure, because of course you, at the end of the day, you say, okay, I'm gonna let's say I'm the attacker, and I'm gonna steal your Bitcoin. At the end of the day, I sit and make a simple calculation with myself. I say, okay, this guy has 1 Bitcoin. I'm gonna steal from him, but I need to, for example, let's say, pay 50,000 for my electricity bill. You may wonder, you may say, how, for example, the electricity bill may go that big. Here is the observation. Let's talk about few encryption algorithms that we know. We have the DES, that it's key. Here is the important thing. The DES that is key is 56 bits. So the key space is 2 to the power of 56. We have triple this with this number of bits for the key. And we have AES, or advanced encryption standard, with this number of bits for the key. Okay. And this table shows the number of trials that we need. 2 to the power of 56, it is approximately 72 peta operations. So if you want to break a DES encryption algorithm using the brute force, you need to apply on average half of this number, which is 3.6 times 10 to the power of 16. That I call it 36 peta operations. 36 times, sorry, 36 times 10 to the power of 15. 10 to the power of 15 is called peta. So 36 peta operations, assuming having a computer in hand, that computer can do 1 billion decryptions per every microsecond. You need something about 1 year, 1 full year for that computer to work. And this is a pretty tough computer. Even our processors that we have in hand, even now today, they can't give us this type of efficiency. We at least need, for example, 10 computers to work in parallel to get something close to this. So you get 10 computers working in parallel, and they need to be worked for this amount of time. So you see, if the key size, for example, is 128, you're gonna get your computers working for this amount of years. And of course, it costs you something. So the cost of brute force attack, now we see that sometimes when I said that you have a Bitcoin 40,000, I'm gonna steal it. So if I do that simple calculation, it makes sense that I say, okay, I'm gonna pay this amount of years electricity bill to let my computers work, to find and extract your key in order to let me steal your Bitcoin. So it's gonna be very costly to me. That Bitcoin doesn't, it's not worth it to me because it cost me more than that one Bitcoin to just find your key. And the same thing, when we say that the goal of cryptographic algorithms is to make or increase the cost or time of finding the key in a way that would cost to the attacker more than the value of the protected information, because that's going to be enough for us for keeping our data secure. And here, like I said, here are the numbers. You can look at it. This column assumes that you have a computer that can perform 1 billion decryption per microsecond, which is, like I said, is pretty high. Our computers cannot do something like this. And this is the same thing, but it assumes a stronger computer, 10 to the power of 13 decryption per every microsecond. So with that, with a computer like this in hand, you can break into DES in 1 hour, which is, of course, it means that it should be a supercomputer, or it might be, for example, 1,000 computers working in parallel. Okay, based on what I said, we define two types of security for in the cryptographic domain. We say conditional cryptography and unconditional, conditional security and unconditional security. In unconditional security, the security is absolute. A ciphertext, uh, an encrypted data cannot be broken regardless of the time or the computational ability that the attacker has. He or she cannot apply the brute force. The brute force is not applicable here. We have a few encryption algorithms that they feature like this. One-time pad is one of them. And in contrast, we have conditional security. Conditional security means, for example, AES, DS encryption algorithms. They all feature conditional security. It means that if I'm an attacker and you give me infinite time and infinite computational power, I would be able to break into that algorithm, and I would be able to discover your secret key. And of course, through that, I can steal all of your information. So it means that they are secure upon some computational powers and cost that you can afford. If you until to some point, if you can afford any dollar amount, I cannot guarantee for some dollar amount that encryption algorithm is not secure anymore, or the data that kind of the ciphertext which is produced by that encryption can be broken. And I'm going to talk about this a little bit more because the first impression this gives us is that, okay, conditional security ciphers or encryptions that they give us conditional security, they are not good. But this is not true. There are some examples that makes this clear. For example, let's say your sensitive data are your credit card data, and you're gonna save them somewhere secure, and of course you don't want anyone to get access to them. Yes, that's true. But how long do you want to keep that data secure? There is a lifetime for that security requirement. I would say for a credit card information, maximum 10 years. Because of course, for a period like 10 years, you will be your expiration date will arrive, and they'll issue a new card, and the information on the card will change. So you don't need to protect your credit card information more than 10 years. So 10 years is enough. let's make it kind of more reliable, 20 years. You don't need to protect your credit card information more than 20 years. So any algorithm that can protect your data secure against available computational power, it should be okay for you. It should be it should kind of keep you safe. Or for example, let's give you another example. Social security number is a very important piece of information for everybody's in everybody's life. But how long that information is important? Isn't it true that we say that that information is only important in the lifespan of that individual? Yes, that's right. If, for example, if I have the SSN of a person who has died, let's say, 20 years ago, what can I do with that? Nothing, because the person is, everybody knows that that person is died. So it's, that information is no longer sensitive. So that's this feature applies to many of our secret or sensitive information, and we can say that many of them, they have expiration date. After some date, they are no longer sensitive. This gives us the ability to to somehow defend from the conditional security ciphers or encryption algorithms. We can say that they're not bad, they're basically good, and we can take advantage of them. And the good thing they give us is that if you agree that you don't need a pure or unconditional or absolute security, if you accept that conditional security might be good for you, in that case, you give option to the developer that they can establish a balance, or they can establish a trade-off between the security and the efficiency. So I don't need to, in that case, I don't need to make the security or encryption algorithm very tough or very complicated, because I just want to make sure that the encryption can kind of stand for 10 years or 20 years. So I don't need something super complicated. So I, as a designer, can trade or can make a balance between the efficiency in terms of speed, in terms of size, in terms of hardware resources that encryption needs, and from the other side, the security. Okay. Okay, what I'm going to do next is to talk about the maybe one classical cipher, which is called shift cipher. This is a classical encryption. Of course, it's not being used, but I just want to show it to you, and then show how it works. And then after that, we get into the actual or real world symmetric key encryptions. We start with DES and then with AES. I think that should be enough for today. Thank you for making today's class, and have a good day. Take care, guys. Bye-bye.